So yesterday we looked at the entire RAG workflow. We went through the program. We saw how we can create a small legal bot which can actually answer a company's questionnaire or like a company specific answer based on company specific data. And we made an LLM answer based on company specific data which is not available on the internet. So we saw the whole workflow, like we take the documents, which could be HR policies, finance policies, or like whatever domain you want to build the chatbot on, whatever is the specific data you want the bot to answer questions related to, we take those documents, we chunk them into smaller pieces, then we embed them, convert them into vectors, store it into a vector database. Then this is the indexing flow. This whole thing is an indexing flow. It happens one time. Then the user queries start coming in from the chat application. The queries are converted using the same embedding model. And then we retrieve top 5, top 10 articles from the vector database and then pass the context to the LLM. So the articles which are fetched from the vector database are fed to the LLM. And then based on the user query and the articles which we have from the vector database, the LLM can answer the user query. Okay, so this was the whole workflow. This is the whole workflow of a RAG system, and we saw it the implementation of this whole workflow altogether. Okay, so today what we will be doing is I'll be discussing some practical points on how or some practical points on different parts of this workflow which I have experienced while developing RAG applications, which might help you, like how can we chunk data, what are the bottlenecks while chunking the data, how does actually a vector database work, and all those things we'll try to cover in today's class. So we'll keep the session in such a way that we will today only discuss practical parts of it. Like these are some pain points that you will experience when you are developing a RAG related application. Okay, so let's get started with it. So we'll be discussing practical points on chunking data. Okay, that's the first part. The flow that I'm discussing is like when you take the documents, right, and you chunk the documents, which is breaking into smaller pieces, what challenges can you come across? Okay, so first of all, what happens, like when you have a document like a blog post or article or a book chapter, right, the text is continuous, right? Let's say if you have a PDF or a blog post or an article, the text is very continuous, right? Sentences flow into paragraphs and ideas build on top of each other linearly, right? So in blog posts or PDFs, sections are properly divided, right? And ideas are like one by one. There is a proper blob of text which flows between the sections, and it's very standard, right? No problems over there. So then in that case, the chunking strategies that we discussed, right? Splitting by tokens, sentences, or paragraphs with overlap works well, right? Uh, but think of an example wherein, like, let's say if you have tabular data, right? Tables, CSVs, and spreadsheet, right? How will you chunk it, right? What are the problems that you will face? So let's say if you have a 500 row CSV, then if you chunk it by character count, or if you chunk it by like 100 rows one at a time, what will happen is the data will be cut into two different parts, and you will lose the header information. Okay, and then what will happen because of that is the relationship or the context of the data will be lost, right? So for example, let's say if this is my CSV data, right? This has some information and I am building a RAG workflow wherein this is the document and I want the bot to answer based on some CSV data that I have ingested. Now, if we have to chunk this particular document, right, what will happen is, like, let's say there are 1,000 or 20,000 rows over here, right? So maybe probably one approach could be you could take 200 rows at a time, split it into one chunk, then 200 rows at a time, and then 200 rows at a time, and store it into vector database. But what will happen over there is, like, when you chunk the first, like in this case, right? Let's take an example that it has 6 rows. Now you are splitting it into 3 rows and 3 rows, right? Chunking. So what happens is, like, when you split the first 3 rows, you can see that the header information will be over here in this first chunk, right? In the second chunk, only this data will go in, right? So it will be hard for the so when we do a semantic match, right? Here from this particular chunk, the LLM will be easily able to infer the data because we have the header information that this particular field is a full name. This is the company name. This is the email of a person. This is the personal touch point or something about this person, right? But when the second chunk goes into the data, goes into the vector database and a semantic matching happens, what happens is the system will have no context. What is this data talking about? What is it actually, right? So when you ingest any CSV data, this is one problem that you can come across, right? So the solution of this is we should always do table aware chunking, right? What does it mean? Let's say if you split the table into 20 to 30 rows, small enough to fit into an embedding window, right? We'll split the whole CSV into 20 to 30 rows. Based on the CSV size, we'll split the rows into these many rows. And then what we will do is we'll prepend the column headers to every subtable so that each chunk is self-contained. Okay. What it means is, like, when I'm doing the chunking, when I have divided my CSV data into this one part and the second part, in the second part also I will prepend the header information, right? So what the benefit we will get from that is, whenever the matching happens, the second chunk also has the context of like what the data is related to. Okay. So when you are building such applications, right, you will hit these bottlenecks, right? You will have CSV data, you will have PDF data, you will have data from the database. So you have to, based on the data type, you have to look at the data and prepare the data in such a way so that when you are storing it into a vector database, the relevant information should go into the database. We should take care of that part. So I'm just taking some common formats of data and how you should chunk or pre-process that data so that meaningful information is stored into the vector database. Okay. So if there is a data in the form of CSV, spreadsheet, or tables, right? Tabular data also, you should do it in this way. So if you have 500 row CSV, you will split it into 20, 30 rows based on your size. And then maybe in each row, you will prepend the column header section. You will prepend the column headers so that the contextual information is maintained in the chunk, right? We should also include table metadata like table name, which is the source file where it's coming from, the sheet name, description, and all those things, right? Yesterday, we saw, right, when we store any data in vector database, we store data plus its metadata, right? So that we store the chunk, the data, and the metadata as well, right? So we will follow this particular process, or when we try to chunk CSV data. Okay, so this was one type of format. Now let's say if you are ingesting a PDF into a vector store, right? Sometimes you might have seen, right, in our company, the Confluence, the data is in the form of like Confluence pages or PDFs or anything, right? So there are also they are not just like text data, right? There might be images also in them, and those images also have like some vital information in them, right? Like, let's say if you have a documentation, let's say if I'm building a chatbot which is related to which is a support bot which helps support people to answer based on troubleshooting the product, right? So now what will happen is, like, what can happen is that in the document which contains steps to resolve an issue, right? What can happen is you can also take a screenshot of some code or something and tell that, okay, this is how you resolve this particular issue. Now you are ingesting the PDF, and the PDF has text plus some image, right? Image has the main information over there that how the issue should be resolved, right? But when you are ingesting, what will you do? You cannot easily parse the images, right? Text you can parse and create a chunk easily. But let's say if you get an image, how will you handle it? Okay. So there are different, so the initial problem is when we chunk the data, right? And when we convert it into vectors, we use embedding model. We saw that yesterday, right? So the general embedding models which are present in the market, right? Which like the one from OpenAI called text embedding 3 small, they only understand text. So when an image comes, they will ignore it, or you can't just feed it into your vector database because it will not be able to translate the image into some form, right? So now we are stuck because, like I told you the scenario over there, right? Your support bot would need that answer from the image, right? In the troubleshooting docs. So how do we handle such kind of scenarios? There are two things which we can do. Is first thing is option A is captioning, right? I will tell you what lossy means, but first thing we can do is we will take that particular image, and during the parsing phase itself, I will pass that image to a vision model, right? Like GPT-4 or Claude or anything. And what we will tell is describe this particular image, right? Or we will pass the image to an OCR and we will tell that describe that particular image, right? Now when the model, once you get the description of the image, right? Now during the parsing or the embedding phase, you will take that description and feed it into the vector database. So that is one approach that you can take to solve the problem, right? What did you do? You were parsing a document, an image came in between. what did you do? As soon as you saw an image, you make an LLM call to one of the models which can understand images, right? And you tell that model that give me a description of the image. So the model, what it will do is it will give you a description of the image, that this image means this, or you pass it to an OCR, optical character recognition, and that will tell you what this image is about, right? So in that whole document, now along with text, you got the image description also, and now you feed it into the vector database, right? So this is one way of solving the problem. And these kind of problems you will face when you like build the RAG workflow in your company, right? So you send it to the vision model. So the vision model, like for example, I take this particular image, I send it to any of the OCR or the vision models, and it gives me back this description, a bar chart showing quarterly revenue for 2024. Q1 is 10 million, Q2 is 12 million, Q3 is 15 million, Q4 is 18 million, right? It gives me what is the image containing, right? So it's now equivalent. I am not losing any information. I can store, instead of the image, this data will go into the vector database. Okay. So this is how you can solve. Other thing which you can do is you can, when the model that you are using, right, for embedding, what I mean is like the embedding model that you are using while chunking and storing it into the vector database, you can use a model which is like multimodal. What does multimodal embedding model means? It can understand images as well as text. So you now don't need to take the image and then convert it into a text. If you need to, you feed the whole entire document. The model is capable of understanding text and images, and it will easily understand what this image is, and it will take the whole context. Like if your PDF along with the, if your PDF is like, let's say like this, right? You have you have one header, which is like header one, and then you have some text and this particular image, right? So now what you're doing is you are ingesting this document into the vector database, right? So now if you use a multi-modal embedding model, what happens is you can take this particular chunk itself, and the model is capable of understanding what is text and what is the image. So it will capture the whole context over here. Okay. And the first option was when you see this chunk, you take this image, you pass it to a specific model that you do it. Okay. And then get a description of this text and replace it over here and then store it in the vector DB. The only when will you do captioning? When, let's say, you cannot use a multimodal, right? In companies, you will not have access to all the models. You will be given only certain models that, hey, our company supports this model. So based on if it's a multimodal or not, you will have to take a call that I should go with captioning. If your company provides you multimodal embedding models, then well and good. Go. If it's multimodal, then you don't need to do this step. You directly feed the whole document, and the model itself will take care of creating the embedding. Okay. So these are two most common problems that you will face while developing a RAG application. You will encounter CSV data, table data, spreadsheet data, and those PDFs, when you are ingesting, they will have images also. So now we know how will we handle these problems, okay, on a high level. Okay. Now there are some other tricky data types also. As a developer, you might know that what can happen is like, again, taking the example of a support bot, right? I have a PDF document which contains the troubleshooting step, and I'm creating a support bot via the RAG. I'm creating a support bot that uses the RAG architecture. So first step, what we have to do is we have to take the PDF and index into the vector database for creation of the support bot, right? So now some other tricky data types, what can come is like troubleshooting steps can have some JSON data as well, right? That let's say if I can have a problem that this API is not giving me correct response. The data is in the form of this JSON data, and there can be some troubleshooting steps, right? So how will you ingest the JSON data, right? Maybe if you don't use the correct chunking strategy, right, it can break, right? So how should we ingest JSON data is, whenever we see JSON data, we should break it down into some small form, into this format, right? Let's say in JSON, we generally have nested format, right? User is an object, then you will have bot address, and then you will have like some address, and then inside that you will have city, right? So what we should do is generally we should flatten the JSON object and then ingest it so that LLM can infer what's going on and we don't lose the context, right? Similarly, you can have code data as well, right? In the PDF document, you have a code and you have to ingest that data also, right? So in order to make the code chunking of the code meaningful or useful, you chunk by functions or class boundaries, right? Not token count. Like let's say if I have a code base, right? What we should not do is like not treat the code base as a blob of text and chunk it like I have a repo. It has this file 1, file 2, file 3, right? File 1 could have function 1, function A, and file 1 could have function 1, file 2 could have function B, right? and now function B is calling function A. So there might be some logic that function B is using and getting results from function A. Now during the chunking, right? If I separately chunk file 1 and separately chunk file 2 and store it into the vector database, while retrieval, LLM might not get the whole context, right? Because they are separate chunks, right? So what we should do in case we get a chance wherein, or there is a requirement when we want to chunk code, right? We should chunk by functions or class boundaries, like class by class or function by function. And generally, we should use apps. We should create AST, right? Abstract syntax tree, and then chunk the data. You can read more about it. Because this is not a common use case, I'm not covering it, but in case you can, like people nowadays creating support bots which can answer your product questions or which can troubleshoot your code is common. So that's why I'm letting you know that if you are building a RAG application where you have to chunk the code, then you have to use an abstract syntax tree and then maybe chunk the data and put it so that the logic, the chunks are created logically and the meaning is intact, right? If you have a document which has some audio data, right? So what you will have to do is, audio is a frequency wave, right? So it LLM, how will you put it, right? You will get like encoded data, right? If you take an audio file and just chunk it, you will have some data which does not make any sense, right? If you open audio file, it will be in the form of like encoded information, some Greek, Roman, something like, like this, right? If you have seen an audio file. So this will not make sense, right? If you index this into vector database, does not make sense, right? So what you will do is, and one example, where this can come into picture is, like, let's say you are building a RAG application where what you do is, you have a team and there are many KTs in the team, right? So the KTs are over Zoom call, or like somebody has recorded some meeting and they have given the KT on a Zoom call. Now we have the voice data, right? And now you are building a RAG application that I have ingested all the KT information. I have a chat bot which can look up which can look up the recordings and answer any question that I have, right? Let's say you are going into a new team and the team has created a chatbot, and that whatever the team works on, that knowledge or the KT is or the KT, the chatbot answers your question. So in that case, when you develop an application for that, then you can also get audio files and you will have to chunk the audio files. So in that case, what we use is, we use services, transcribe services, right? What transcribe services do is, basically they can read an audio file and convert it into text, right? So if you're building an LLM bot wherein you have audio data, you should use a transcribe service, convert that audio into text, and then chunk and store it into the vector database, right? So you understood this use case, right? When will audio data come into picture, right? I took a very similar, like a simple example wherein like the use case will be something like this, right? I'm just making this up, that there is a team, right? The team works on some microservice or some concept, right? So any new member which onboards into the team, right? He has to be given the KT. Now the manager tells you that develop an application or a chatbot so that we already have these KTs. The team member does not have to go through all the KTs, knowledge transfer. Okay. Instead, we can build a bot, and the new person who is onboarding can ask questions to this bot, right? Develop an application. So what you will do is, whatever KTs we have from the team member, right? You will create a RAG application for that, right? So you will take the KTs which are present from all the team members, right? You will take the docs and you will store it into the vector database, right? So what I was saying is, these KTs are in the form of audio, right? So what you will do is, you will take all these audio files, convert them into a text service. Services are available for this, right? You don't have to write your code on your own. There are certain software services which are available. You will take that text, you will take the audio files, convert them into text, and then store them into vector database, right? And now the onboarded member or the new member, what they can do is, they can type in the query and that will be converted into embedding, and you can then look up the vector database. So this is an idea of a small application wherein like audio can also come into picture while developing the RAG workflow, right? So now I have taken a clip of one more thing to show you how complex the chunking part can become, right? So this is a newspaper article. See over here, when you chunk this information into a vector DB, how will you chunk it? So there are so many, it is so difficult to chunk this part. How will you chunk it? Whether you will take this whole part and do chunk the whole data from here, or or because when you read a newspaper, right, how do you read it? This is the article, then this is one section, this is one section, this is the other section which follows this section, and this section is over here, right? And then the fifth section comes over here, right? Whereas in general, when we see general PDF data, right, or there is no layout, there is just information which is like one paragraph over here, next over here, next over here, next over here, so on and so forth. So when we chunk, I pull up this data, right? In the next chunk, I pull up this data, and in the next chunk, I pull up this data. What I'm trying to say is, let's say if you come across a scenario in your company wherein you are given research papers, and the research papers are like in this format. So this is first paragraph, this is second paragraph, this is third paragraph, and the fourth paragraph is over here. So normal chunking strategies will fail over here, because they will just pick up this they will try to pick up paragraphs like this, right? Which might be wrong. The information is flowing like this from here to here and then here and so forth, right? So in these kind of strategy, when you chunk these kind of articles, you have to look at the layout, the reading order. Everything is very important, right? So the point being, whenever you are doing chunking, right, your RAG flow is as good as your chunking strategy. If you chunk the documents correctly, then only LLM can give you right answers, right? So if a problem like this comes, then just the point being, you have to first go through the documents, see what is the structure, and then come up with the right chunking strategy. Okay. One repo which I just wanted to point out, which I have used and it's really good for chunking strategies, is this Surya OCR. Okay. This Surya OCR, it supports like layout detection, reading order, and everything. So if you are using chunking, maybe you can take a look at this repo and see how you can leverage this, because it supports all this layout detection, reordering order, reading order and stuff, so that you can chunk your documents correctly. Okay. So this was all about chunking, the practical tips, what challenges you will face. So creating prototypes is very easy. You will create a basic prototype and then you will get the answer and it's done. As soon as you try to take this RAG application into production, you will hit these chunking issues and all these workflow issues and all. So you have to be really careful on how to handle these, right? So the data preparation should be very accurate. Okay, so this was chunking strategies. Okay, now a very popular interview question is like, how do vector databases work, right? We need to understand that part. In the previous class, what did we saw is we, instead of traditional databases, since we are storing vectors, we will use vector databases, right? But we should also know how do actually vector databases work internally, right? So I'll give you a high level overview. It's very important to understand how vector databases work, because then you understand the whole end-to-end workflow properly. And it's also an popular interview question. When you go in for any applied AI engineer role or something, this is a popular interview question. Okay. So how do vector databases work? So what is the problem, right? First and foremost, how are vector databases different from relational or NoSQL databases? Okay. So imagine you have 10,000 documents, right? And somebody asks the question, how do I reset my password, right? A normal database like SQL, what it does is it searches by exact matches of word, right? Now, it searches by exact matches of word. So for example, if I type in a question that how do I recover your login credentials, right? So what will happen in traditional SQL databases is, right, I have stored all the information, 10,000 documents, and now I want to search how do I recover my login credentials, right? The document has one of the documents in this 10,000 documents has this information. Sorry, I think I mixed this two up. My query was, how do I reset my password? This is my query, and my SQL database has this information in one of the documents, recover your login credentials, right? So what will happen in SQL is, when you try this query, right, it will not fetch this document which has this information of recovering your login credentials, right? Why it cannot do it? Because traditional databases, they do a word by word match, right? Here, see, how do I reset my password and recover your login credentials are the same, right? The user query is, how do I reset my password? In the 10,000 articles that I have in my SQL database, I have this information, how to recover your login credentials. But word by word, they are not matching. So SQL will fail and it will say it will not return any data. Okay. So this is the problem of SQL databases. This is where like vector databases come into picture, where they search by meaning, not by exact words, right? The underlying semantic meaning of how do I reset my password and recover your login credentials are same, right? SQL will fail, but vector database will pass in this scenario, right? So that is why we use vector databases, okay, because they are capable of doing semantic search. So this is why we use vector database. Now, what is the core idea of vector database? How can they do semantic work? Semantic matching is they convert each piece of text. They take any data, the chunks that we give to it, whether it could be image, audio, etc. And then they convert it into a list of numbers which capture its meaning, right? We saw during the when we were reading about LLM or the transformer architecture, right? The second phase is the embedding phase, right? Where what we do is we take certain words and embed it into numbers. You can go back to the notes and see how these numbers capture the meaning, right? So now what we will do is we will take, let's say if I have a blob of text, how to reset password. I convert this into a number and recover your login. I also converted this into a number. All the 10,000 documents that I have, I will convert them into numbers and store it over here, right? Now see this number, how to reset password and recover your login, right? These two have very similar vectors, okay? Very close by vectors, okay? So if I have to point them into a n-dimensional vector space, how to reset password and recover your password, right? They are very close to each other. So because their meaning is very same, right? So this is what vector databases do. They store vectors and then they store the semantic meaning of the sentences. And then they do a search. When a new user query comes in, they see where can the point lie. So for our case, recover your login credentials will lie somewhere close over here. So it can understand what is the meaning over here and what is the article related to this, and it will give back the article. Okay. So the core idea of vector databases is taking text, converting it into vectors. Vectors are numbers which contain the semantic meaning of the sentences. Okay. So now what do vector databases actually store, right? For SQL databases, we generally know that they are rows of information, row 1, row 2, and then they have column wherein like one ID could be ID, name, password, stuff like that, right? So similarly, and NoSQL databases have a document format, right, where you store JSON data and all. If you know about it. So these two are the databases. This SQL databases store data in the format of row and column. NoSQL databases stores in the form of document. So similarly, how do vector databases store data? Vector databases store data in this format. Each document will have an ID. Then they will have the vector. Vector is nothing but the numerical information. They will also store the text, right? I have taken this text and converted it into vector, right? So they will also store the text along with the vector, okay? And then the metadata also, they will store the metadata. We saw this, right? While chunking, what do we do is when we store data, we store the vector data as well as the metadata also, like where is this chunk coming from, which PDF file is it coming from, and so on and so forth. What was the name of the file? What is the date of the creation of the file? We store metadata, right? Like that. So in vector databases, when we store the data in this format. ID, what is the vector? This vector we get from this text only. So the vector is there, text is there, metadata, right? Vector field is what we will use for semantic searching. But when we return the data, right, that cannot be in the form of vector. Otherwise, I will have to take this vector and then convert it back again into text. To avoid that, what we do is we store the vector and the text as well. Both the parts are stored so that while I am doing a semantic search, I use the vector field. But when I have to return the results, I can directly return the text field. Okay. Now we already know the vector is used for similarity search, the metadata or the original content. So you can return the real answer and filter the results, right? So now let's take a step back. We know already what a vector database does. It does similarity search using vectors. Vectors are numbers. And one more example which I can give you is like, let's say you have a vector of dog, puppy, and let's say a dog and a puppy. Now, if you let's say if you type in puppy, right, you mean a dog, right? So it can figure out that dog and puppy are same words. So if you have a question around that, it can return that information. It does not have to look up the word, right? So we understood this part. Vector databases, what problem they solve, how do they store the data and all. But one part which is really important is, so let's say if you you are building a RAG application and you are ingesting 10,000 documents. You have to store 10,000 documents, for example, right? Now, when you are doing the query, right? So the problem is, so the problem over here is now let's say in the vector database, you have stored 10,000 or 1 million documents. Now during the query time, you have a query and you want to see which of these documents match the query, right? So will you go and compare with all the 10,000 documents which are stored in the vector database, right? That is a very slow and painful process, right? So what we need to do is we need to somehow index the data. Vector databases also do indexing of the data. And then when a query comes, we look at the index that where can the information be, and then then answer based on that, right? So that is the indexing phase. So the indexing phase is getting data ready to search. So what happens during the indexing phase is, like if my RAG application has 10,000 or 1 million articles, first I will chunk the data, I will embed the chunks, store the vector, and build the index. Okay. So this is the first phase, right? So I'm building an application, like I said, I had said over here, right? When you build a RAG application, this is the first phase, and this happens offline. Okay. First, you have to build the vector DB. Okay. I have 10 million articles over here. I'm building my RAG application. First phase is I will take all these 10 million articles and store it into the vector database. The problem is when the queries will come, will I compare, even to do a semantic search, will I compare against all these 10 million articles? No, right? That will be a problem. It will be painfully slow. So in order to solve that problem, what do we do is first we index the data or create an index of the data, index in the vector database. So we will be discussing about that part, like how do vector databases actually create index, right? So like I already said, the problem is if you have a 10 million vectors and user asks a question, should we compare the questions vector against all the 10 million vectors? No, right? It's painfully slow. The database organizes the vectors cleverly in advance. When you are indexing the documents, it will cleverly organize the data. Okay, this organization is called the index. Okay, so now what happens during index? Okay, so now let's consider this point. You have 10,000, like 10,000. Let's stick to 10,000 articles or 10,000 chunks, right? So how will indexes be created? I'm explaining that part. What vector databases do is, like we have these 10,000 articles. What they will do is they will try to club articles which are same into something called as centroids. Okay, or think of them as buckets. Okay, I have my 10,000 articles. I am ingesting them one by one. So what it will do is, let's say I have document 1, 2, and 3 which have similar context. So I will chunk them into one centroid. I have document 5, 4, 5, 6 which are similar, which convey the similar meaning. So I will convert them into centroid 2 or bucket 2. Similarly, I will create other centroids or other buckets in my document. How will I create these centroids? That is done using an algorithm called k-means. Okay, k-means is used for classification, which means that I take an object, I see what are the categories available in my database, and I will just put it in that particular category. Like animal could be a category, living beings could be a category, non-living beings could be a category. So whenever a new object comes or a new article comes, whatever the categories I have, I will put them into those categories. Okay, these categories are called centroids. Okay, so I ingest my 10,000 articles and convert them into centroids. Okay, now at indexing time, see what happens. What is the advantage of converting them into these centroids, right? I got 10,000 or 10 million vectors in the n-dimensional space. I create 1,000 natural center points or buckets called centroid. What does it mean? Just like the articles which are similar, I create a centroid or a bucket for that. Okay. And like I said, we use k-means algorithm, which is a classification algorithm, which does just classification. What category it belongs to. If I have 5 categories and a new object comes in, I just choose what category it belongs to, right? So now centroid 1 will hold, let's say, 10,000 vectors. Centroid 2 will hold another 10,000 vectors. Centroid 100 will store another 10,000 vectors, right? It is not, I'm just giving you an analogy. It's not necessary that each centroid will hold 10,000 vectors. It is, I mean, whatever docs are similar, it will do an approximation and store those vectors, right? So now what we have done is each one of the 10 million or the incoming vectors, while I was indexing my data, each of these 10 million vectors is assigned to the closest centroid. Whatever was the centroid, I have assigned it to that, right? When I am ingesting my 10 million data, right? Now what will happen during the query time, right? When someone does a query, when a user comes in and types in a query, now I have to search the vector database. Like I said, the problem is I cannot go in and compare my query with all the 10 million articles, right? That will take a lot of time. So now how this centroid structure will help us is the querying will happen in 2 rounds. Okay. In the first round, what I will do is I will compare my query, the user query, which comes in against the 10,000 centroids itself, right? So what I will try to see is the user query came in. I will see I will try to do a similarity search between this, my user query, and this centroid. I will try to fetch the score, right? What is the similarity score? It is 0.31. I will take my query and I will try to do a similarity score with C2 centroid. So I will see the score is 0.12. So, and then so on and so forth. In my vector DB, if I have created 1,000 centroids, I will compare them with all of these 1,000 centroids, right? And I will come to know that which centroid can be closest to my user query, or which centroid can have the answer, right? So I will see that, okay, C2 centroid is closest because the distance between my user query and this C2 centroid is the smallest. So this centroid can have my answer. So the query belongs to centroid or bucket C2, right? Now in round 2, what I will do is now search inside using the winning bucket. So I got to know that C2 was the centroid which was closest, right? Because the similarity score was less. So now what I will do is whatever articles are there in the centroid, let's say 10,000 vectors, then I take the user query and compare with this all these 10,000 vectors. So what will happen now is after comparing with these 10,000 vectors, I will get my information. Okay. So see how, so what did we do? I will explain it once more so that it's very, very clear. I told you the technical part, but let us once take a step back and explain. Let me explain the architecture of vector databases. So what did we do is we are creating a RAG application. Okay. The RAG application is nothing but, let's say I'm building a support bot. Okay. Support bot, what it will do is it should answer my user queries about the product. Queries about my products in my company, right? I have created a support bot with the support, which the support agents will use. Okay. So now the answers for my product or the development team, what they have done is they have created 10,000, they have all the information of the product in these 10,000 articles, right? So when I create the application, what do I do? I chose what I want to do is I want to use vector databases. So first, what I will do is I will take these 10,000 articles and embed them, break them into smaller pieces, and store them into the vector database, right? Now I created the chat application, and when the user typed in, or when a support assistant typed in a query, what I will do is I will try to match it into the vector database, that out of these 10,000 articles, which article has the answer to the user query or some troubleshooting information that the user is happening, right? So this is my application. So I will try to search among these 10,000 articles, which one has the answer, right? So that is what we were discussing. Now, the problem that vector databases solve is when the user query come in, I cannot go and compare along with 10,000 articles. It will be very, very tough. So how vector databases solve that problem? They took those 10,000 articles and maybe divided them into 10 centroids. Okay. Something like this, or 10 buckets. Okay, centroid is the actual technical term, but you can think of it as buckets. This centroid has had 1,000 articles which have similar meaning. This centroid had 1,000 articles maybe which have similar meaning. This had 500, this has 200, and so on and so forth. I divided these 10,000 articles into, let's say, 1,000 centroids. Now when the user query came in, instead of comparing with this 10,000 vector, each of these vectors, I compared the query with these centroid vectors. Okay. So I got to know that C2, the user query or the user troubleshooting, the query which the user is asking or the support person is asking, the article could be in this C2 centroid. Okay. So now I see that C2 is the closest. So I go to now the C2 centroid and I see in the C2 centroid there are 10,000 articles. Now I compare against all these 1,000 articles, right? So this is how we are solving the problem, so that we don't have to do a comparison with all the vectors in the domain. Instead, we take a indexing approach similar to a book, right? In book, what do we have? First, we have indexes, right? Which says that chapter 1, chapter 2, chapter 3, chapter 4, right? And then each chapter contains that information. So if I have to if I have to learn a topic, vectorization, which is in chapter 3, I don't have to go via the entire book to figure out, right, which chapter has it. I can look at the index and tell, right, that my query is I want to read about vectorization. It's in chapter 3. I can directly go to the page number, right, of that particular chapter. Similar concept is happening over here in the vector databases. So this is how vector databases are also there. I mean, SQL also uses the same concept for indexing and solving, but this is how vector databases work internally, and they solve the problem, right? So instead of doing like if my database has like 10 lakh articles, instead of comparing, when a user query came, instead of comparing with all of them, in round one, I did just 1,000 comparisons. I compared my vector, incoming vector or the query vector with 1,000 centroids. So I got that which centroid had that information. Now, whatever articles are there in that centroid, I compare against all of them, right? So in a total, I'm just doing 11,000 comparisons. While if I had done a comparison with all the articles, I would have to do like this 10 lakh comparisons, right? Which come down to 11,000 only. So this is how vector databases work. They are like 900x less work, right? So this comparison or the whatever I spoke about is called approximate nearest neighbor. Okay, so this is what vector databases use, and they all some vector databases use this approximate nearest neighbor. Some use HNSW, which is hierarchical navigable small worlds. Okay, so I will not cover this. This is graph based. Maybe if you are interested, you can go in and read about this. So this is how vector databases work. Okay, so we covered how vector databases work end to end. How do they solve the problem? What, how, why, what, and how. We covered all these parts. Okay, now let's come into the final part of RAG, which is like when should we use RAG and when should we use fine tuning. Okay, so what did we learn during fine tuning? We learned that we can train a model so that it can answer, the model can answer based on my company data, right? My company data was, the LLM model was not trained on company data, right? So I can fine tune the LLM model so that it can look at my company data and it can also answer that, right? In RAG also we saw the same flow, right? What did we know? That LLM is not trained on my company data. So instead of training the model itself, what I do is I come up with this RAG architecture, which is where I store, wherein I use a vector database. I store my company data in the vector database, and when a user query comes in, I pick up the relevant articles via semantic search, because I have now this capability of doing semantic search instead of keyword. And then I pass the articles plus the user query to LLM, and the LLM can answer, right? So now we have two approaches. So when should we use what is what I wanted to make clear. Okay, so now let's say if your use case is there, right, and you have to take a call whether I should use the RAG architecture or I should fine tune the model, right? So so you should take these points into consideration, right? Let's say if the frequency of the knowledge, you should consider the frequency of the knowledge updates. So if you have your documents and they are getting updated every now and then, every 1 month, 2 month, or so on and so forward, so on and so forth. Like let's say if your company has some, you are creating a bot for your company which employees can use to get some data that has HR policies, finance policies, so forth and so forth. And this HR and finance policies are updated by the HR team very frequently, every 2 months and so. So in that case, you should not use fine tuning. Why? Because fine tuning takes a lot of time. It's not very useful. You have to every time go in and keep fine tuning the model with the updated knowledge. That is very, I mean, it's not very easy to do that. So if the frequency of knowledge change is very high, we should not use fine tuning. We should use RAG, because in RAG, what we will have to do is it's very simple, right? You keep on ingesting the newer documents. You find a delta between the change of the documents, and you keep on ingesting those newer documents into the vector store, and you don't have to change anything in the model, and your chatbot can still answer those questions, right? So if the frequency of knowledge change is very high, then you should not use fine tuning, because fine tuning is best for static knowledge, right? If when you are creating a bot for domains such as legal or medical, where the information is not changing very frequently, then you can go for fine tuning. If your documents or your information is changing very fast, such as financial markets, then you should go for RAG, not fine tuning. Okay. Cost and computational requirements. So in fine tuning, you know, right? Fine tuning is taking the whole model. The model is very big with so many parameters. It requires GPU of training and all. So in that case, fine. In this case also, we should, if your company does not want to do computationally expensive computation, and it requires high performance GPUs, so you should not go for fine tuning. You should go for RAG. RAG is more cost effective as it avoids the need for continuous model retraining, right? Instead, it relies on external knowledge bases, making it a scalable option for AI-driven companies. Okay, so we have seen that if the frequency of knowledge is changing, we should go for RAG. If we don't want to invest it too much, then also fine tuning is an expensive process, so we should not go for it. We should go for RAG. latency and performance. So if you have a requirement that I want the answers from my chatbot or the application that I'm building pretty fast, I cannot tolerate low latency, right? Then you should go for fine tuning. Because RAG, you see, right, I'm querying a vector database, coming up with that information, although I'm doing some optimizations over there, but there is an additional hop of querying the vector database, and then the LLM looks up answers based on that, right? So if latency is your major concern, right, then you should not go for RAG. You should fine tune the model. Okay, you should not go for RAG. Okay, because RAG adds a additional hop. It increases the response time by 30 to 50%. Okay, and if you should also consider accuracy and hallucination risk. Okay, because if you want your bot to be highly accurate, like let's say if you're building a bot for a medical field, and you cannot you cannot I mean have hallucinations or less accurate information, then in those cases also you should go for fine tuning, because in fine tuning it reduces the risk of the hallucination, because model actually learns those facts, right? We are making the model learn everything from external sources, while RAG is doing approximation, right? It's trying to do a semantic search wherein, like, based on your strategy, it can fail or it can pass. RAG is less accurate, fine tuning is more accurate. So if accuracy is a concern, then you should go for fine tuning, not RAG. Okay. So this was all about RAG and fine tuning. Now we have taken a look at how the RAG architecture looks like, what is RAG and what is fine tuning, what are the caveats or what are the problems that you will face when you are creating a RAG application, and how should you handle that, and how does a vector database works internally, end to end, the whole architecture, what algorithm it uses. We have seen all that. Okay, so I think we are good for today. I will keep it till this point. In the next class, we'll start with agents.